All righty, friends. Welcome back. Welcome back. Today is the last day that we introduce any new derivatives. After this, there's no more new derivatives from here on out. But before we get to it, we need to go back and review a couple things. So, got to go back and review a little bit about what we know about Arctrig. So, Arctrig is really nothing more than inverse trig. So when we think about Arctrig, we think about inverse trig, I don't care what the trig value is, like for instance, arcsin of x. That's really the same thing as sine -1 of x. The only difference is, and it's not really a difference, but we want to make sure we do this, is that we limit the domain. So we're going to go back real briefly here, and we're just going to look briefly at a couple functions. Just so we're aware of why things are the way they are. Take the idea of sine. So sine can go in a positive direction, or it can go in a negative direction. So this is the value of -2 pi. This would be negative pi. 0, we got, here's pi right here. And we have 2 pi right here. Now remember, when we're talking about inverse functions, they can't just pass the vertical line test. In order for the function to be invertible, we also need to pass the horizontal line test. So in order to do that, it has to be able to get through both. Let's see if I can make that a little bit smaller. So that domain is the domain that we are using when we're dealing with arcsin. That domain is us going from -pi/2 to positive pi/2. And we'll clarify that here in a second. Let's keep going through cosine here. Remember what's going on with cosine. Cosine goes down and then up. These are the graphs of sine and cosine. So right here with cosine, we have our -pi/2, we have negative pi. We have -3 pi/2, we have -2 pi. And then pi/2 and pi. 3 pi/2 and 2 pi. So when we're dealing with the domain to find the inverse of cosine, we went from 0 to pi. So that means my inverse of cosine, or my arc cosine, is going to be anything from 0 to pi. For tangent, tangent wasn't too bad. We like tangent. We just took one period of tangent. So in other words, we just went from one vertical asymptote to the other vertical asymptote. And we said that one looks like this. And if we go from one asymptote to the other asymptote, it wasn't that big a deal because one period of tangent passed the horizontal and vertical line tests. So when we were looking at our functions in, when we're dealing with arcsin, we came back to the unit circle. And by the way, this is also the same thing as arc cosecant as well. When we came to these values, we didn't do every single value on our graph. We went to and we stuck from negative pi over 2 to pi over 2. Anything that didn't fall in that region, we called that the no-go zone, the no-fly zone. We don't go there. So we don't want anything. We only want everything that goes from negative pi over 2 to pi over 2 because that's what passed both the vertical and horizontal line tests of the original function. For cosine, or arc cosine, and also then for that matter, arc secant, we only wanted from 0 to pi. We didn't want everything again. We just wanted the stuff that fell on our domain. So anything from 0 to pi. So anything below that, when we were dealing with arc or inverse, we didn't deal with those. So these went away. We only dealt with quadrants 1 and 2. So arcsine and arc cosecant, we dealt with quadrants 1 and 2. Arc cosine and arc secant, we dealt with quadrants, I said that wrong, didn't I? 1 and 4 for arcsine and arc cosecant. 1 and 2 for arc cosine and arc secant. Then for arctangent and arc cotangent, again, we were back to dealing with quadrants 4 and quadrants 1. And so we had to limit our domains for these trig functions. And again, I know I already said it, but these are things that we kind of looked at last year when we had these as an essential skill for ourselves. We dealt with keeping the domains to a certain area. Tangent and cotangent had the same domains as sine and cosecant. All right, so we didn't go into any of these areas over here. So before we actually started looking at just a little bit with how this is going to apply to trig, do a couple of these just to make sure we have it. So friends, what I want you to do is I'm going to give you some arc values. I'd like you to go ahead and evaluate what these are. So go ahead and pause the video as soon as we're done here and see what you guys can deal with these. Of -2 and arctangent of √3. All righty, go ahead and pause the video and then we will come back and talk about it. All right, so when we were dealing with arc again, we started off here, we drew it, we got in our no-fly zone, we said, all right, can't be over here. This is bad news. So we looked at it and said, okay, well, when is the y value equal to -√2/2? Well, that happened over here at 7 pi over 4, but we didn't want 7 pi over 4 because that would have caused us to go around the unit circle. So we had to go backwards to get negative pi over 4. That's coterminal to 7 pi over 4. So we said that's negative pi over 4. Likewise, arc secant. So first thing we did is we went ahead and we drew in our no-fly zone there. Try to figure out where we couldn't go. So arcsecant is the reciprocal of arc cosine. So if arcsecant is -2, arc cosine is -1/2. Well, that happens up here. That would have been 2 pi over 3. So that's just, again, we just need to make sure that we know our unit circle as we go around it. And then our last one here, we have an arctangent. We get our no-fly zone. We're going to have to draw that in here. So no-fly zone, can't go over here, off limits. So tangent of root 3, that will be up here. That happens at pi over 3. So the answer would be pi over 3. This is a real just quick review on just evaluating ratios using arc and being able to determine those angles. The biggest thing to remember is that every time we're dealing with an arc, that's actually an angle. So let's take this one step further. What is this going to do for us, friends? Well, let's go ahead and give ourselves some function. We'll just give ourselves a sine. And then when we're dealing with the inverse of sine, that's the same. We'll go and let that be some g of x. So the inverse of sine is going to be arcsine. Or sine to the -1. So arcsine and sine, they're inverses of each other. So if we remember the derivative for inverses, the derivative of an inverse function that's the same thing as 1 over the derivative evaluated by the inverse function. Well, what if we were to use this with trig involved, trig in mind? If we were to do that, friends, we end up, if say I wanted to find the inverse of sine, the first thing I'd have to do is I have to figure out what is the derivative of sine. So if we come back here, the derivative of sine, again, this takes us all the way back to the beginning of the year. The derivative of sine is cosine. So we have our cosine of x. But in this case, we don't have our x in there. We have our inverse function, which is arcsine. So let's just take that arcsine for a second and see if we can't figure out what that actually looks like. Arcsine is the same thing as, oopsie, pardon about that. Arcsine is some sort of angle. So the angle that it's representing is sine of theta equals x, or the same thing as x over 1. Well, if I were to draw that triangle there, I get opposite over hypotenuse. And friends, do a little Pythagorean theorem, I'm pretty sure I get 1 minus x squared. So when I'm saying cosine of arcsine of x, what I'm really saying here is that is the same thing as cosine. The adjacent, or cosine, would be the adjacent over the hypotenuse. So we end up with 1 minus x squared over the hypotenuse, which is the same thing as 1 over 1 minus x squared. So essentially, we can go through and using what we know about arcs and what we know about the derivative of an inverse function, we can use that to determine what the derivative would be for some arcsine function. And we can use this idea then to come up with the derivative of every single Arctrig function. Now, I'm not going to go through and prove them all for you, and you guys don't have to do it yourself, but I wanted you to at least see what's going on here. So that way we're not totally confused about where these are coming from. We're just using combining a composition of Arctrigs, which we did last year in pre-cal, with the derivative of an inverse function to be able to get our derivatives. And so here's our last derivatives of the school year. So we just got this one, but now instead of using x, I'm going to use f of x here. Arcsine of f of x equals the derivative over the square root of 1 minus f of x squared. And if I were to keep going through here, let's go derivative of arctangent. Of f of x. That would be the derivative of f prime of x all over, and again, we could go through and prove all these if we wanted to, but we don't really need to. As long as you know kind of where one of them came from, that's how we would go through and generate all of them. D over dx. And let's do arcsecant. This arcsecant is kind of an interesting one. It's an interesting little derivative. But again, we'd still prove it the same way. We get f prime of x. And again, you guys also have all these derivatives at the front of your Schoology page. So and this would be f of x squared minus 1. And it turns out all the co-functions are the exact same ones. It's just instead of having f prime of x in the numerator, it is the negative f prime of x. But other than that, everything is the exact same. So let's see if I can write these up here real quick so you guys have them. And then we're going to be playing with these for the last little bit. Probably should have just used u instead of f of x, but that's all right. So the negative inverse of f of x all over 1 minus f of x squared. Cotangent is going to be tangent, but again, it's going to have the negative up in the numerator. So for the cos, you just basically take whatever the original function was, or whatever the original derivative is, and just put a negative in front of it. And the last one, if I can fit it, this one might be kind of tough to fit. Let's see if I can do it. Arc cosecant of f of x. Gonna run out of room here, friends. And we end up with the derivative again, a negative derivative, all over the absolute value. I think it's kind of fun to have that absolute value out there. And f of x squared minus 1. And I did run out of room. I was worried about that. Actually, no, I got it. Okay. So these are our last 6 derivatives. So what we're going to do is we're going to play with them today. So we're just going to see what we can do with these. And then we'll do a couple quick applications with it, and then we will call it a day, and we will not learn another derivative for the remainder of the year. So let's try one here. What if I ask you guys to find the derivative of f of x equals arc cosine of 3x minus 4? So all we're really doing here on this is we're just picking the correct, derivative, and we're just evaluating. So in this case, my f of x, this would have been my 3x minus 4, so that's my f of x. So that's what I'm going to use for f of x. So my derivative then, in the numerator, I have negative f prime of x. So f of x is 3x minus 4. F prime of x is 3, because it's linear. So it's going to be a negative 3 on the top, all over the square root of 1 minus f of x squared. So if you notice, this right here, that's my f of x. And this right here, that's my f prime of x. At least the 3 is, that is. All right, so all I'm going to have you guys do is I'm going to have you go through here and just come up with a couple derivatives for inverse. Now, they don't, I haven't seen them have you guys ever do too much with these, so we're not going to play too much with it. But just so that way you are familiar with it in case you do see it. Arc cotangent of cosine of x. Find the derivative of that. And then also go ahead and find the derivative of, well, let's try arcsecant. Arcsecant of x squared plus 3x. All right, go ahead and pause the video and see what you guys can come up with. Go for it. All right, arc cotangent. Let's see, that one's going to be right here. There's arc cotangent. So here's my f of x. So we're going to go ahead and plug it into our derivative here. So on the bottom, I have 1 plus my f of x squared. So f of x again was cosine of x. And then on the top, I have negative times the derivative of my f of x. So if f of x is cosine of x, the derivative of that would be negative sine of x. And we'll clean that up just a little bit. All right. So let's see, I have my, right here, my f of x function. And I'm dealing with arcsecant, so that'll be that one right there, my horrible handwriting. All right, so f prime of x. I first start off my absolute value of f of x in the denominator. So x squared plus 3x. Times f of x squared minus 1. So that would be x squared plus 3x. And then the derivative of f of x would be in the numerator, so 2x plus 3. So we don't do too terribly much with this. We just are going to go ahead and just kind of clean this up. I'm going to rewrite this first one here, just make it a little bit easier to see here. Because that was kind of sloppy there a little bit. So if anybody is having a hard time seeing it, let's see if we can actually just clean that up. So we have 3x minus 4. And the derivative of that is 3. So that's where all these things kind of come into play. So we're dealing with derivatives of Arctrig functions. We're not going too terribly crazy. Just wanting to play with them a little bit here. Determine the equation of the tangent line to f of x equals arcsine of x minus 2 plus 3 when x equals 2. All right, let's try this here. Can we maybe apply it to one more kind of idea before I give you one final problem here? So what if I ask you to do the tangent line? I know the x value. What I need to know is I need to know the y value that it goes with and the derivative of it. So let's deal with the y value first. If I want to know what f of 2 is, I plug it in here. So arcsine of 2 minus 2 plus 3. So f of 2 equals arcsine of 0 plus 3. Well, arcsine is 0, so I'm going to have to go through and figure out that value real quickly. Arcsine, I know I can't go to the left side, so that's gone. So arcsine is 0. That's when my y value is 0. Well, that's going to be right here at 0. So that means f of 2 equals 0 plus 3, which is 3. Okay, so we got our point. Now we need our derivative. So to find our derivative, so arcsine, that would be this one right here. So we plug in everything here. Let's see, I have a square root of 1 minus. And we're going to plug in our f of x. So there's my f of x right there. So x minus 2. The derivative of that positive 3 at the end is 0, so I'm not even going to worry about that. So there's my value. So f prime of 2 equals 1 over the square root of 1 minus 2 squared. So f prime of 2 is 1. So I got my slope, got my point. Let's go ahead and write the equation of our line. So y minus y1 equals m times x minus x1. There we go. All right, so we can do it just like we were able to do with all of our other derivatives. We can still deal with equations of tangent lines. And then everybody's last and favorite thing. Because we want to make sure we can still do all of our applications. Determine all of the relative extrema for f of x equals arctangent of x squared. All right, well, sadly, friends, we've reached the point where this is probably the last time I'll be singing this song for the remainder of the year. We're going to say what we're going to do. We're going to do the work, and when we're done, we're going to say what we found. So let's do it. So relative extrema can exist when f prime of x equals 0 or when f prime of x is undefined. So we've given ourselves permission to go ahead and deal with the work now. So we say what we're going to do. Now we're going to do the work. So I'm going to start off by giving myself a derivative. So arctangent, this will be 1 plus squared. So my f of x is x squared. I'm going to plug that in here. So there's x squared. And then the derivative of it is on top. So when I clean it up here, now I can set it equal to 0. That's what I gave myself permission with my initial statement. So 1 plus x to the 4th. So 2x equals 0. So we have a derivative. When x equals 0, the derivative equals 0. What about if it's undefined? Well, no, because that's going to give us into imaginary numbers, and we aren't going to do that. So that'll be gone right there. That's not going to happen. So we do have a relative extrema, though, at 0. So we got to figure out at x equals 0, what happens. So we pick values before and after it. If I plug -1 in here, I'm going to end up with a first derivative that's less than 0. If I plug a 1 in here, I end up with a first derivative that's greater than 0. So all of a sudden, friends, I have a relative min at x equals 0. Which means, in order for me to deal with my relative min, I better figure out what the y value is for that. So f of 0 equals arctangent of 0 squared. So f of 0 equals arctangent of 0. Now I got to evaluate arctangent of 0. Do that real quickly. Whoop. Whoop. And again, we have a no-fly zone here. So we're not coming over here to this area. Which means, just like we saw before, arctangent of 0 is the same time when when sine is 0. So that's going to happen at 0. So f of 0 equals 0. So at 0, 0, I have this relative minimum. So we said what we were going to do. We just did our work. When we're done, friends, we say what we found. F of x has a relative minimum at 0, 0 because f prime of x changes from f prime of x less than 0 to f prime of x greater than 0 at x equals 0. Well, friends, that takes care of derivatives for the entire school year. And we'll talk about this a little bit more tomorrow. And tomorrow night, we will deal with our last integrals of the school year. All right. Take care.